Okay, yeah, so maybe let's start. Good afternoon. What I would like to do in the lecture today is, in a way, tell you about developments that took place sort of over the last 15 years or so, which have to do with the fact that interactions in ultracold atoms are very short-ranged. And a standard approximation is to say, well, it's zero range. There's no, we neglect the range of the interactions. And I mean, everything what interests us is happening far beyond this range. And what people use technically is the so-called pseudo-potential approach, which goes back in the context of sort of superfluids to the old work by Huang and Yang in '57, but actually sort of dates back much earlier to Fermi, the Fermi pseudo-potential in the '30s to describe, for instance, neutron scattering, beta piars, and so on. So these things have been sort of known for a long time, and it has been used after cold gases were sort of realized experimentally. It has been used, I mean, essentially throughout, but in a way, the consequences, the full consequences of the fact that you can set the interaction range to zero, essentially through a very good approximation, have not been exploited. And it was, in a way, in 2005, starting with a bit mysterious paper by Tan, but very deep and insightful, that people realized, okay, there is more that can be taken from this. And the fact that the interaction is of zero range leads to a number of exact relations, which are relations that hold independent of the state of the system, even for strong interacting system, that such relations can be derived, exact relations that relate experimentally measurable quantities with each other, and have found a number of applications. And I will only sort of, in a way, discuss in detail one of them. Now, to start, I want to start with something very elementary, which, of course, I think all you know, is basically if I look at ideal gases, quantum gases, and discuss, I mean, what's the behavior of their correlations at short distances. And if you take the density in a uniform system, the density at a point x and the density at point 0, and you look at, then this term has, or this correlation function has a self-correlation term, which is the first term with the delta function. And then in a uniform system, there's a dimensionless pair distribution function G2 of x, which can, of course, be easily calculated for ideal gases. And it has a behavior which is indicated here on the right, which I think most of you know, that namely that for bosons, this function, which tells you about sort of you fix a particle here, what's the probability of finding the conditional probability another one at a distance x, shows some bunching in an ideal Bose gas, even at high temperatures. It goes up to 2. If this ideal Bose gas undergoes Bose-Einstein condensation, then in the ground state you get a function G2 which is identically equal to 1, while in a Fermi gas, single component, of course, two fermions of the same kind cannot be at the same point. So basically you get a hole here, a Fermi hole here, and the Fermi function goes to 0 at the origin. And this, in a way, the change here for bosons from 2 to 1 was something that was stressed in an influential paper by Yuri Kagan, Boris Vistonov, and Jora Shlapnikov in the beginning of sort of cold gases. They said, well, of course, if this bunching is gone in a BEC, that also means that sort of, for instance, two-body losses will be reduced, because the probability of sort of two particles being together is reduced by a factor of 2. If you talk about three-body losses, then it's even a factor of 6. And then they said, okay, that's a beautiful story. Namely that, in a way, we get rid of much of the losses, or quite a bit of the losses, by going from cooling the gas through the transition temperature, something that had been sort of experimentally seen then soon after BC was realized. Can one measure sort of this, in a way, reduction from, well, ideally 2 to 1 in a BC? Now, there is one way that sort of was pioneered by the group at the Institut d'Optique Chris Westbrook and Alain Aspect with metastable helium-4 atoms, where you can release them from a trapped cloud, let them fall in gravity, and then from sort of a sensitive detector, which allows you essentially to detect both time of arrival and space, you can, in a way, reconstruct what the probability was for two atoms to be close together in the original state. And this is a well-known result from sort of, well, more than 15 years ago now, that you see as a function of separation, there is some, of course, there's not the perfect, you don't see it goes up to 2, but you see there is some bunching going on above TC, while in the BC, this function is essentially 1. Similar results had been obtained by Tilman Esslinger and Michael Köhl at DTH using a BC in a cavity at around the same time. So I mean, for ideal gases, I mean, this is very simple. And what I want to discuss now is, in a way, what's happening with interactions. I mean, how do interactions change this picture? And can one say, in particular, something that goes beyond sort of some weak interactions? Now, it's clear that if I take repulsive interactions for bosons, then even in a BC, I mean, they will tend to avoid each other. And so the G2 will be sort of less than 1 because correlations, repulsive interactions will reduce. So there will be this, in a way, bunching will be reduced. And the question is, I mean, can one do this quantitatively and describe this in an interacting system? Now, one case where you can do it in a way in full glory, if you wish, is one dimension. If you take bosons in one dimension, moving in one dimension, and you assume a delta function interaction with some characteristic length A1 here, which for repulsive interactions is negative, then one can work out what the G2 of 0, the probability of two of these bosons to be at the same point, is from the derivative of the energy, essentially, with respect to this parameter, which was introduced by Lieb and Lieniger in their exact solution of the 1D Bose gas. And this function at sort of 0 interaction, so gamma is equal to 0, is just 1. But then if you crank up the interaction, this energy saturates, and this G2 of 0 becomes smaller. And this is something that was predicted by Dima Gangard and George Laplikov in 2003, and measured, so the suppression of the G2 of 0 with repulsive interactions was measured then 2 years later by Kinoshita in the group of David Weiss by looking at the rate for photoassociation, where you take sort of two atoms in the continuum with a stimulated transition form a molecule, and this rate with increasing gamma, which at that time you could essentially increase by twisting the one-dimensional configuration, namely the confinement. You increase the confinement, that in a way lowers this A1, increases the strength of the interaction, and then you go from a regime where this function, the G2 of 0 is, well, a bit below 1, here you see on the logarithmic scale, to a regime where essentially you reach what is called the Tonks-Girardot gas, where this correlation actually goes to 0, like 1 over gamma squared. So this is, and there's beautiful agreement between theory and experiment. So this is the 1D situation, and what you see here from this is that in one dimension, the G2 of 0 still makes sense. So this is a nice, in a way, continuation of the ideal gas. It's just now repulsive interactions reduce it below 0, and eventually, in a way, the system for strong enough repulsion even behaves like a fermionized system. Two bosons with short-range repulsion do not want to stay at the same point, and the G2 of 0 goes to 0 eventually. Now the question is, I mean, can one do something similar for interacting gases in 3 dimensions? And if you look in the literature, there's not, I mean, in the old literature, there's not that much on this. In the sort of fundamental paper on, in a way, going beyond Bogolyubov by Li, Huang, and Yang in 1957, they actually showed that if you use a pseudo-potential, they mostly talk about hard spheres in that system. They show that, I mean, this G2 at short distance, short means here now you approach the diameter of these hard spheres. This G2 is just at low enough densities where they could treat it, is just the square of, here what you see is the zero energy two-body wave function. So what Li, Huang, and Yang realized is the G2 at short distances is just the square of the two-body wave function. And the question is, I mean, can one, in a way, extend that to arbitrary kind of interactions? And also, in a way, does that expression also make sense if you apply it below the sigma or so, below the hard sphere diameter? For hard spheres, of course not. I mean, hard spheres cannot be closer than sort of their diameter. But if you say this is something for a pseudo-potential, the pseudo-potential is just a zero range potential, then it should also be fine. But you see it blows up. And so this is, in a way, brings me to the outline of the talk. I will show and I will indicate what sort of the preferred method of deriving such relations is. It's a method that comes actually from high energy physics, namely that there is a series of exact relations for many body systems with zero range interactions. So of course the fundamental assumption is we can neglect the range of the interactions. We can use a pseudo-potential. And then what I will show is that the G2 of 0, which you know well, and which of course, I mean, has, I mean, for photons is of course a major quantity to describe sort of correlated states of photons, is actually ill-defined in dimension 3 and must be and is replaced by a dimensionful property, namely the contact density. And then I will actually list a few examples where this contact density shows up, and it will discuss then an application of these methods to a non-trivial and for a long time sort of not well understood situation, namely if you try to measure the excitation spectrum of a Bose-Einstein condensate at reasonably large momentum in a regime where interactions become strong. As we will see, this experiments, old experiments that have been done first at Schiller and then later on in Cambridge, can be explained to some extent with these methods, but there are still open questions. That's something that, I mean, is still not completely sort of understood. So let's start with, in a way, describing a many-body system with zero-range interactions. And at the two-body level, we know that, I mean, the two-body scattering wave function, which you sort of use as a boundary condition, Bethe-Bayer's boundary condition, to define the scattering length, has a form which I write here now in a somewhat unusual form. You, of course, know a scattering wave function at zero energy is 1 minus scattering length divided by r. Now, I multiply this by minus 1 over a. You say, why? Well, I mean, it's just a constant factor. I do it because, you see, this can also be used if the scattering length is infinite. Then this is a well-defined thing. While sort of the usual form of the two-body wave function, if the scattering length is infinite, sort of doesn't make sense. So I take this form as sort of the two-body wave function. But now I have to deal with the many-body problem. And I want to know, in a way, what's happening if two particles come close together. And this is, in a way, where, I mean, this technique of the operator product expansion that was developed by Wilson in high energy. Of course, the high energy guys always look at short distances. That was clear. But it was also developed in statistical physics by Kardanov and then Brizin, Saint-Justin. I mean, they have used this quite extensively in statistical physics. But I will, of course, not go into sort of the details of what the relation there is. Essentially, you're setting the length, the lattice constant to 0. So if I try to describe the annihilation of two atoms at nearby points, so I have a center of mass coordinate x, and I have a separation r and a separation x, which I want to go to 0. Then, in a way, this is the basic assumption is that you say, well, if they're close together, they feel only the two of each other. And the rest is just some spectator. And this spectator is described by some operator psi of r. So this is an assumption at the first point. You say, okay, I can expand such a operator product at short distances by the wave function in free space, two-body wave function, times some operator, which, okay, at first sight I don't know, and then, I mean, maybe expand this to higher order, but here I am happy with the first 2 points. So this is an example of what is called an operator product expansion. Then we have two operators at nearby points, which I label A and B, and then I expand this out in local operators O sub L. And in principle, there could be many, or there are many of them. And then these coefficients here, these are called the Wilson coefficients. They are C numbers, not operators. They depend, of course, on the type of operators I have and sort of what the operator L that appears here. And they depend in some way on X, typically with some power in X. So this is an example or the general form of an operator expansion. You may know operator relations, the Baker-Campbell-Hausdorff formula, e to the A, e to the B is something like that. The question is, what distinguishes this from such an operator expansion? The answer is, Baker-Campbell-Hausdorff, this is exact for any operators, whatever you want. This here is also an operator identity, but it holds for eigenstates of a specific Hamiltonian. For all eigenstates, but of course it's not a relation which, I mean, has the generality of Baker-Campbell-Hausdorff. It holds for eigenstates of a specific Hamiltonian. Now, if we take this and now apply it to our problem of determining what is the short distance behavior of the density correlation in an inhomogeneous system in general, then if I exchange psi and psi dagger by commutation, then I mean the leading term is the density itself with a prefactor which is a delta function. So you can say the leading term in this operator expansion of this product is just a delta function times the density at this point. But then the next contribution comes from, in a way, this term, and I square it and I get the psi daggers. So in the end, you end up with something which gives you a square of a two-body wave function times the product of these two operators. So that's a very simple way of deriving this thing. And I call now this the expectation value of this guy, which is by definition positive, the contact density. What I see here is then, since this my wave function squared is just, I can square it out very easily, I get a result which is in a way consistent with what Li, Huang, and Yang had told us a long time ago. But what you see here is, since I normalize things in such a way that there's a 1 over r and a 1 over a, the two leading terms are 1 over r squared minus 2 over ra. So in this form, it was first written down by Tan in 2005. Note here this dot 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 terms, these are order 1 corrections, but they cannot be determined from this level of expectation. So how does, according to this relation, the pair distribution function of a BC look like? Well, at the non-interacting system, the G2 is just trivial 1. If I look at large distances, I have the particles tend to avoid each other, and you see it approaches 1 from below with a minus 1 over r to the 4th behavior. And that involves sort of the Healing length. Then there's this term, minus 2 over r, but then you see this is a positive term, 1 over r squared. And then you get, so this tells you that, I mean, there's a bunching here, if you wish, and in principle, sort of, I mean, you see, if you really exploit this down to 0 distance, of course, G2 of 0 doesn't exist. This diverges very badly. Actually, this behavior was first realized in a paper by Narashevsky and Glauber in 1999. They, however, in a way said, well, there's this term here, which in a way gives rise to an increase of the G2 at short distances and some bunching, but it happens since they assume sort of weakly interacting BECs, it happens when the scattering length is of the order of the van der Waals length. That's sort of the typical value of the scattering length. And therefore, they said, well, I mean, this is not really a relevant regime, because as long as the scattering lengths are of the order of the van der Waals lengths, you don't see this blow up. But of course, if the scattering length is, I mean, separated from sort of the real short distance scale, which I have set to 0 here, then, I mean, there is this bunching, and this will sort of have some experimental implications. Now, if this was sort of the only thing sort of which we can get from this method, you say, well, this is nice and interesting, but it's not really that super exciting. It just tells us that the G2 of 0 is not defined, and there's this bunching here. But the real deep story that, in a way, was started by Tan in 2005 is that the same quantity which determines the two-body correlation function at short distances appears in many, many other quantities. And there's a number of exact relations, and I will give only a small example, or a few examples of this list. The most prominent one being that the same C2, and this is why sort of we had the 16 pi squared before, determines the fact that if you look at the momentum distribution of this system of bosons at large wave vectors, meaning sort of wave vectors larger compared to the sort of interparticle distance and other thing, there's always a 1 over q to the 4 power, and the coefficient, the strength of this is also determined by the C2, same quantity. That's not immediately evident, and maybe sort of I can indicate why this comes. This comes if you look at the momentum distribution. We know the momentum distribution is the Fourier transform of the one-particle density matrix. And if I now try an operator product expansion of this product, then you would say, well, just Taylor expand it. If I set x to 0, then I get the local density, apparently, psi dagger psi. Then the next term in the Taylor expansion is plus I over h bar times x, and then it's the momentum density operator times r. You know, I mean, momentum in quantum mechanics is psi dagger gradient psi minus complex conjugate. That's this one. And now the question is, I mean, does this go on simply with x squared and so on? The answer is no. The next term turns out to be mod x divided by 8 pi times this phi dagger of r, phi of r, which is, say, psi dagger, psi, psi. So in the expansion of psi dagger psi, there's a term which has 4 operators. And that guy is the expectation value is the C2. This contact density, as I've shown before. And you know, if I have in the real space a mod x, if I get in Fourier space a 1 over q to the 4th. So this is a way to see this thing. And this is completely universal. I mean, for zero range interactions. It's a very, very general thing, which, I mean, in a way, the old people in this field have missed completely. Although they saw a q to the 4th behavior, but they didn't realize that the coefficient was something that had physical meaning. Okay, so this is one of the relations. The other one that was, in a way, realized very early on by Felix Werner, Laetitia Taruel, and Yvonne Castin is that actually you can determine near a Feshbach resonance, the closed channel fraction is also related to this C2, which I will not deal. You can relate, and this was the Tan, the so-called Tan adiabatic relation, you can relate this C2 essentially to the derivative of the energy with respect to 1 over A. So thermodynamically, the C2 is just a conjugate field with respect to changes in the scattering length. You can also show that, I mean, the clock shift and the asymptotic decay of the RF spectrum is related to this two-body contact density. This is something that we did early on with Matthias Punk. And you can, in a way, now extend the come back. The two-body losses and also three-body losses with this C2. This goes, you have two-body losses when the two-body scattering length has an imaginary part, and the rate for this is determined by this coefficient C2 precisely in this very simple manner. So that's in a way recovering the qualitative results of Kagan et al. That basically, okay, the probability of having two guys together is determined by this C2, and in this relation you get the two-body decay rate. So these are a few examples that show that this contact density appears in many observables, and there are quite a number of others. I'm not able sort of to deal with this. I want to show in a way now two experiments which actually measured this. So there's, of course, you can say I measure it from the decay of the momentum distribution and other observable quantities, but I think sort of two very nice clever interferometric measurements of the contact were done in recent years for 3D Bose gases, actually near unitarity by the group of Soran in Cambridge, and in two-dimensional Bose gases here by the group at the Collège de France last year in 2 dimensions. So let me first start with sort of, what do you theoretically expect is? Since I showed that the contact density is related to the energy with respect to 1/A, we know the contact density where we know the energy. When we know the energy, how does the energy depend on A? That determines the contact density. Of course, we cannot derive that for arbitrary strong interactions, but at least for dilute BCs, just from the mean field result for the energy, we know that the contact density at 0 temperature is just essentially the square of Na squared. We also know by a virial expansion, at high enough temperatures, the contact density goes like n times the thermal wavelength squared. Essentially you can infer this from dimensional arguments. The contact density must appear at order n squared. You need at least sort of two particles to be close together. And then, since it has dimension centimeter to the fourth, that's the only thing that can happen. And the corrections with interactions, as long as the magnitude of the scattering length is much larger than the thermal length, are just minus 1 over lambda t over A squared. And this was measured in a very nice way by Richard Fletcher, and one of the authors is also sitting here, Rafael Lopez, by saying, okay, I start out with, in this case, a gas of potassium 39, where you change the blue state is sort of essentially non-interacting. You change by a pi over 2 pulse this into a coherent superposition of the blue and the red state. This coherent superposition evolves because sort of in the red state there are strong interactions. So this precesses, and then by a second pi over 2 pulse you match, in a way map the phase evolution here into a population imbalance. From this you can infer this precession rate. And the precession rate again is proportional, turns out to be proportional to this contact density. There is a term here which essentially, if you replace this contact density with this mean field term, this is just a mean field shift which appearing. But there is also a term which comes from sort of 3 bosons interacting. And the term which involves the 3 bosons interaction, you see, has in a way dimensionally is 1 over centimeter to the 5th, and it survives even at infinite scattering length. At infinite scattering length, the C2 is finite, but the A is infinite, so this term is gone away, but this term survives. And what they were able to do is essentially, in a way, measuring this as a function of magnetic field through the Feshbach resonance, and you see this essentially, this curve here, the red curve here, is just the second line here. So it's n lambda t squared. Prefect is 32 pi, which is 100 essentially. Very perfect agreement. And then you verify this relation in the moderately degenerate regime quite nicely. And you can also sort of qualitatively infer that the 3-body contact actually scales like density cubed. Similar method was used here at Collège de France. Jérôme Beugnot, Sylvain Jean and collaborators last year were able to measure a very small change in the clock transition frequency by also transferring atoms into a state which has different interactions in state 2 than in 1. The change in scattering length is very tiny, 5 or 6 Bohr, but then this was enabled a small shift here of 20 Hertz was enabled them to determine this contact as a function of the phase space density. So here on the right, it's just essentially a perfect BC, where so the normalized contact is just 1, and then it just goes up, and essentially you can see this is a perfect realization of now the effective G2 of 0 goes from 1 to 2 at reasonably high temperatures, meaning low contact density. Now, this brings me actually to an interesting point, which so far is not, we had some discussions here about this. In 2 dimensions, in a way, the fact that eventually sort of this contact density, as it does here in 3 dimensions, becomes small again at high temperatures cannot be seen in this quasi 2-dimensional situation, because you would need thermal wavelengths that are so short that you are out of the regime of essentially quasi 2D situation. But if you have a 3-dimensional gas and if you have a homogeneous situation and would measure at a fixed density the contact as a function of temperature, what will happen, or what must happen, is that it has a maybe small value at low temperatures. It increases, will have a maximum around the BC transition temperature, and eventually goes down again. Both theoretically and experimentally, this has not been seen so far, although it's, surprising even for weakly interacting BC. Now, before going to a rather sort of more intricate application of these short distance correlations, let me say something about sort of historical precursors of this. Markus Viertz, this is the Viertz from Pauli and Viertz, in 1957 wrote a paper about what is the equation of state of a hard sphere gas. And what he derived is that 3 times the pressure of this hard sphere gas is 2 times the energy density plus a correction, which involves the curvature of this two-body correlation function right at contact with some energy here. And it's proportional to n squared. So of course, if you let the density of this hard sphere gas go to 0, this term goes away. And then you recover 3 times pressure is 2 times density. That is, of course, the relation we expect for an ideal gas. And as we will see in the next lecture, that's a relation that holds quite generally as a function of scale invariance. But the fact that a hard sphere gas has a finite radius breaks scale invariance, and this term can be seen sort of as a trace anomaly. Now, for hard spheres, of course, the G2 is identically equal to 0 below the hard sphere diameter. So you must have a situation or a behavior where you have the G2 of R as a function of distance. And if there is the hard sphere diameter here, then there is no way of getting 2 particles closer than the hard sphere radius. But then at this contact, it starts with a square. Well, why? Because the wave function vanishes linearly. We know all the wave functions are at an infinite vanish linearly at the box. And so the question is, okay, what can we say about this curvature? And this is described at the thermodynamic level by this old result of Viertz. Now, it's an easy matter to show that essentially from this structure, you can, the non-analytic behavior of the two-body distribution function at contact implies that the momentum distribution of a hard sphere gas has a power law tail. But of course, now the power law is not sort of at 0. It's not a pure power law. It's modulated by sort of sine q sigma squared. And this coefficient here is essentially given by this curvature. And in particular, what you can also show is that if I take the limit of the hard sphere radius going to 0 and assume that, or take the limit that this sigma squared times this hard sphere contact are finite, then I recover the time relation. So if Fierz would have gone a bit further, not too far, he could have described this in 57. I mean, this is just a simple consequence of these things that, I mean, I've detailed a bit in the lecture notes. And interestingly, sort of the fact that you have this power law decay with some oscillations, there are numerical results for momentum distributions of hard spheres. They show some oscillations. Whether they are consistent with this, I have not checked, but okay. And in particular, sort of the LHV result is just that this dimensionless contact just approaches 2, but then at higher densities will become larger. Now in a way, rest of the talk, I will discuss an application of these relations on Bragg scattering, where you try to, or not, where you essentially determine the excitation spectrum of a BEC. So this is a schematic setup of Bragg scattering, which I took over from a paper by Chris Vail, but where you have sort of two lasers with sort of different wave vectors and frequencies, and they provide a moving and spatially periodic perturbation in the BEC, which couples to the density of the BEC, and you can show that in linear response, the rate of momentum transfer in such a situation is proportional to the imaginary part of the density correlation function at this difference frequency and at the difference momentum up to some frequency squared. So this has been used early on, Bragg scattering, to determine the excitation spectrum of BECs at MIT and by Bill Phillips, and then by Jeff Steinhauer and Neil Davidson at the Weizmann Institute, and I show sort of the results of the Weizmann Institute. The excitation spectrum of a BEC is what you expect and what you have learned in a way from Bogolyubov theory. There's a linear spectrum at low frequencies, which goes over to a quadratic spectrum at higher frequencies, and the crossover appears at the inverse healing length. So, and what you also see here is that, I mean, the free particle spectrum are just the dotted lines here. And you see, even at relatively high frequencies, there is some offset here, a shift with respect to the free particle spectrum. And I will be concerned with what is this shift and how does it evolve with interactions. Now, to remind you, of course, the simplest approximation to describe sort of excitations in a BEC is the Bogolyubov approximation, where essentially at low enough densities compared to the scattering length, you describe the whole interacting system as a bunch of harmonic oscillators. That's all, with an excitation energy which is has this form, you know, from Bogolyubov theory. Now, what Bogolyubov theory tells you is essentially, of course, that, I mean, for a given momentum, there's a given frequency. There's a one-to-one relation, and there is no other choice for frequency. So basically, this tells you that the dynamic structure factor can have, at a given momentum, can have a peak only at one frequency. So Bogolyubov immediately implies that there is what is called a single mode approximation. This spectrum has a delta function, ideally. And you can fix the prefactor of this and also the form of the excitation spectrum just by using some rules. Now, of course, in Bogolyubov theory, we know is of course for weakly interacting BCs. The question is, I mean, is it valid beyond? Now, the answer is, and this is a deep result by Feynman, is that this approximation is not an approximation if you are at small momenta. It becomes exact. There is nothing else. At small momenta, this is exact, at arbitrary interaction strength. This was shown by Feynman because the simple density excitations exhaust the full spectrum. But at large momenta, of course, I mean, one doesn't know. I mean, there is certainly, this is not exact, but Bogolyubov tells you, okay, there's a one-to-one relation between Q and omega already also at large momenta. And of course, if you apply this Bogolyubov formula, which essentially divides the free particle spectrum divided by the static structure factor at large momenta, then you get at leading order the free particle spectrum, and there's a shift g times n. the 2 goes away with the square root, and then it's g times m. So this is precisely this shift here. Now, already in 2008, the Chiller group, Eric Cornell, Carl Wyman, I think it's the last paper where Carl Wyman was author on a physics paper, and Debbie Chin, measured this, used this method to determine sort of the excitation spectrum at reasonably large momenta with rubidium-85, where there's a nice Feschbach resonance where you can change the scattering length. And they determined the line shift, which they expected just a shift away at large Q from the single particle energy. And they expected this to be sort of given by the mean field shift, and therefore sort of if you add a given density and a given wave vector of your modulation is expected to increase linearly in A. So the data are shown here. The blue line is for a short scattering length, 100 A Bohr, and you see a peak here. And then if you increase the scattering length by a factor of 6, it shifts to the red. So there's a blue shift. Okay, that's something that you expect. But somehow then they went to about 900 A Bohr. This is as far as they could get. And then, I mean, quite surprisingly, sort of this got back again. I mean, it became wider, but the blue shift sort of in a way, well, became smaller again. Why? So there's a down, so here you see sort of the line shift as a function of the scattering length at fixed Q. It starts linear, but then sort of has a tendency to go down where the width just increases linearly. And so there's a downturn of the line shift near QA of order 1. Now, in much more detail, this was investigated by Soran's group a few years ago with Rafael Lopez as the first author here with potassium-39 in a box, where they essentially measured this line shift as a function of scattering length for different densities. And you see, indeed, there is this downturn of the shift, and it becomes even negative if you go to low enough densities where you can increase the scattering length. Here you see up to sort of 3000 A Bohr. And at the lowest densities they could reach, then, I mean, where the QA went up to even 7, you really see, wow, it goes down, it becomes very strongly negative. So in a way you get a spectrum which is in a way much lower than sort of, I mean, what you expect from your single particle peak. Now the simplest type of sort of idea that, for explaining this was to say, okay, recall our short distance behavior of the two-body correlation function, which of course, I mean, if we recall the relation to the static structure factor, implies that the static structure factor from 1 over r squared, if you Fourier transform that, that gives 1 over q. So you get a C2 1 over q. And from this you get a minus 1 over q squared contribution. And so just from these two terms, if you use the single mode approximation, you get a non-monotonic shift. Namely, you get Bogoliubov at QA much less than 1, and then you get a correction minus, which is linear in Q, but of course which changes sign and then goes down. The corrections here are order 1 over Q, so at large Q I can neglect them. And this is the result which is shown here sort of as these solid lines. So you see here in this regime where the QA is over whatever up to 2 or 3, it works quite well. This simple, what they call Feynman-Ton. But it doesn't work at all at large Q. Here you see sort of Feynman-Ton would actually sort of give you with increasing Q or increasing QA, a more and more negative shift. I mean, that's certainly not true. So what's going on, and what's sort of in a way the physics of this negative shift? I mean, why suddenly sort of do we get excitations in a way below the single particle energy? And the physics, I believe, is sort of in a way quite different from this story. The physics has to do with old things that in a way, I mean, Hohenberg and Platzmann started in the 60s in understanding scattering on strongly interacting gases in the regime of high momentum transfer. At high momentum transfer, you can say, maybe I can neglect sort of the interaction. I just assume I have a certain momentum distribution, and from this momentum distribution, I take out a particle with energy k and transfer it to energy k plus q, to momentum k plus q. And this is just the kinematics of energy momentum distribution. This approximation here is actually the analog of what Feynman and Burkane later on developed for sort of the parton model of deep inelastic scattering. You describe the proton as consisting of non-interacting fermions, and then say there's a distribution function of sort of how many fermions, many of these constituents have a certain fraction of the proton momentum, and then you apply sort of basically particle kinematics, and then you get a certain type of scaling, which in high energy physics is called Burkane scaling. Here, it's known, it's a certain scaling, where the scaling function is determined by this momentum distribution, and the scaling function is the deviation from the energy in units of Q. What this approximation predicts is that you get a symmetric peak centered around the single particle energy, and the line shifts, I mean, this is just sort of the width here, are linear in Q. But this will never give you a negative line shift. What's going on? Well, what's going on is that if you are working at high momentum, you may transfer your momentum not only to a single particle, but to 2, 3, and so on. Then things are very different. Imagine sort of you transfer a given momentum q to 2 atoms, and I, for simplicity, do it symmetrically on both sides. Then, of course, depending on the alpha here in between, I can get a complete continuum of spectrum. The least energy I get when I sort of have a collinear process, where I have sort of q over 2 in the same direction. Then, since the energy is quadratic in q, the energy starts at the free particle energy over 2, a factor of 2 below the energy, and you can go up to arbitrary high energies, of course, if you have a bad angle. And in particular, so you see there's a different scaling of the width. Here it's q, and here it's q squared. So I mean, these two approximations, or these two things, are sort of completely different. And so the question is, I mean, can one derive or develop a theory which describes the whole story? And I mean, actually, this can be done. This is something we have done with Johannes Hoffmann. You have to sort of extend this operator product expansion to also time-dependent problems, so you expand at short distances and short times, and you look at sort of what kind of operators appear here. This is essentially, in a way, you know, the Nobel Prize 2 weeks ago was given to 2 people developing climate models and to Parisi. Parisi is cited for complexity, but actually sort of the fact, I mean, Parisi got famous in the first place for doing this, namely deep inelastic scattering, developing sort of the, in a way, operator products expansion for deep inelastic scatterings and finding violations of Burkane scaling. That was Parisi's original sort of fame on that. And in a way, this is in a way similar what is done here. And what you have to, in a way, if you work out this, then this implies a certain 1/q expansion of this density response function, which involves sort of powers of q with increasing sort of delta L. So, I mean, the higher ones are suppressed at large q. And the 2-particle contribution, which I just indicated, is actually proportional to the 2-body contact. And there's a scaling function now, which involves the deviation from the single particle energy not divided by q, but divided by q squared, essentially. And in particular, you can calculate the scaling function, and it's very strongly asymmetric. As I showed you, the onset is now not at, the peak is not here at the non-interacting particle energy, but at half of it. It's a very, very complicated function. And you see, basically, if you have a lot of weight much below the single particle energy, then, of course, in a way, the overall shift can become negative. And in a way, out there, there's a strong asymmetry, and the tail out there was actually discovered by Damson and Thompson already in 2010. There's a power law decay involving the C2 with a frequency omega over 2. Now what you see is this two-body contribution isn't sort of, cannot be the full story, because near the single particle peak it diverges here like 1 over c squared. So what do you need to do is, well, you have to in a way combine both, and I will sort of not discuss, well, okay, it's essentially again saying that this in the single particle excitations have this scaling with 1 over q as sort of the deviation away from the single particle peak. If you work out what is the behavior reasonably away from the single particle peak in this impulse approximation, it's a 1 over the scaling function squared because of the high momentum behavior of the momentum distribution. The operator product expansion gives the same behavior, and actually you can check out this coincides. So what you get is something where you really have the impulse approximation working as a function of inverse q near the single particle peak, but there's a continuous crossover from single particle to many particle excitations, which appears here when this scaling variable is of order 1. So these are these dotted lines. So basically you can connect this impulse approximation to the many particle excitations in a continuous manner, in a smooth way. Now, as I said, does it work? Well, partially, unfortunately only. If we can determine sort of in a way the shift, which has a real and imaginary part, at small QA, it of course recovers Bogoliubov and actually corrections which behave like q squared and not linear in q. At large QA, actually the shift is predicted to be negative, but at a where really QA going to 1, to large compared to 1, the two-body shift is predicted to go to 0 eventually, because the contact density will be finite and there's a 1 over a here. That's not seen. So you see a negative shift here, and you see sort of the prediction of our theory is sort of the dotted line here. So it's doing reasonably well, but not at really very large QA. And so what I believe is, but nobody has checked this, is that sort of, now at this regime, three-particle correlations and higher things become important. They have a tendency of sort of getting into the right direction, but to really work that out is a nightmare. This calculation already was something that was not that easy, and in a way, high energy people have sort of gone beyond Burkane scaling to whatever, 3-loop order and something like that. We have been able to do this only at the 2-loop order, but not beyond. So this is in a way a problem which has some similarities to high energy physics, but in a way it becomes technically so complicated to involve three-body effects that we haven't been able to do it. So this, and in particular also what I want to show is that the full spectrum, you can actually also calculate within some approximation the full spectrum. And so this is shown here in blue. And it has sort of a lot of weight, say at half the free particle energy, then it's near the single particle energy, and it's certainly far from a single peak. So if you would use a single mode approximation, it's not. If you have a complicated spectrum, a single mode approximation does not tell you about this. And so you see this also here in this plot, sort of the free particle dispersion is here, this dotted line, and we have a lot of weight down here. And in particular, if you are sitting at a fixed Q, there's a whole range of energies which are possible, because you transfer momentum not to one particle, but to many, or in principle. And this is, in principle, sort of, if you include n-body processes, you have onsets at the free particle energy divided by n. These are sort of, in a way, collinear singularities, which, actually play a role also in high energy. So this is, in a way, all what I wanted to say. What I indicated is, and I indicated also a bit so how these things could be derived, is that if you have systems with zero range interactions, this approximation implies a lot of exact relations that hold independent for arbitrary states of the many-body problem. Of course, arbitrary means you cannot go to high enough temperatures. Once, I mean, with the S-wave scattering is no longer holds, then I mean the whole model breaks down. But apart from that, I mean, you can use it for arbitrary states of the many-body problem, and they connect short distance and short time correlations with thermodynamic properties, and you can check them sort of in a number of ways experimentally. And then I've discussed this Bragg scattering at large momentum, which I think is important to realize that, I mean, at high momentum, you cannot just use, in a way, single particle excitations. Momentum is transferred to more particles. And there's, in principle, a systematic expansion of this in powers of inverse of the momentum, which roughly explains this negative line shift, which was observed a long time ago and more recently in Cambridge. But the extension to three-body correlations, and also in a way you would like to see the whole spectrum, of course, that would be, of course, a challenge for the future, but of course it's a rather difficult challenge. Okay, thanks a lot for your attention. I'm happy to answer questions.